Right, hello everybody. My name is Andy. I'm a little bit of everything, done a lot of development, done a lot of operations. Obviously securing things is imperative. I'm a co-founder at Control Plane, that is continuous operations for Kubernetes and containers with a special focus on security engineering, but it's still CI with an implementation detail. And I want to talk today about what happens when that infrastructure gets hit by a meteor. What that means for us, what our disaster recovery plans mean, and how we recover from those sorts of events. So let's talk about what happens when one of these hits, for example, Virginia, which transits about 70% of all internet traffic. Impact events can reach the order of thousands of Hiroshimas, but this will apply to plenty of other scenarios too. Casual infernos, unscheduled percussive maintenance, and I feel terrible for that guy, and of course, acts of beasts. And there's a slight experiment going on here with embedding YouTube videos instead of 20 meg animated GIFs. And this looks like it might have failed in terms of experiment. We may be victims of the conference Wi-Fi, so I'll just see if it'll go any faster in parallel with delivering the rest of the slides. So, what does this talk about? Recovering from the inevitable disasters that strike us all, enabling engineers on complex systems, so building out infrastructure that allows operations engineers to experiment with impunity and to deliver infrastructure in more of a continuous integration type feedback loops, tests, in that sort of world, automation, secrets, and making sure all this is done adhering to best practice. I'm just going to change Wi-Fi. See if that works later on. Right, so we're about to have another attempt on the videos, so I've just changed. Okay, so in today's cloud-native world, everything deploys into Kubernetes. And I think you're going to have to accept the fact that that is the best cat meme of Kubernetes that you'll ever see. I might come back to it if we're really unable to get there. So yeah, Kubernetes makes sense for stateless greenfield applications, but maybe not cloud-hosted services or hybrid infrastructure or some stateful services. So what can be done to make deployment of Kubernetes clusters more repeatable, more testable, and more maintainable? Meteor-proofing is an opinionated amalgamation of a number of other techniques that was born from high compliance work with the UK government, with especially high security and resilience requirements, but it's just an evolution of the state of the art and hopefully not too radical. So there are an evolutionary mixture of infrastructure as code, where everything that is deployed starts off as code and is checked into version control, immutable infrastructure, whereby everything is replaced in an atomic fashion as opposed to upgraded in place, and as we all know, software development practices under the umbrella of continuous delivery. It's also a cozy bedfellow with GitOps, operations by pull request, which essentially says if we're checking all of our infrastructure code into version control, then why should we not extend that and do the same thing with our application configuration and the meth configuration, the gray area between what a Kubernetes cluster is running on, or any other scheduler for that matter, and how the application configures its dependencies outside of that cluster. So while GitOps is currently more container-focused, these principles are not constrained by containers in any way. And by applying continuous delivery principles, Meteor-proofed infrastructure can be made resilient to a number of cloud failure cases. In its simplest form, it looks like this. We have a higher order abstraction, like a makefile or any other task runner, that pulls a pre-baked image that contains all of our all of our build dependencies. So that's a Terraform version, that's Ansible with Python 2.7, that's whatever else we need for dev and test cycles, including like a root CA bundle. Maybe we want some Let's Encrypt stuff in there as well for deployment. That code is checked in and built on a build server so that a developer, when the build fails, can pull exactly the same environmental state and run exactly the same commands with the same configuration as the build server. And that removal of the build server as the first verification step means that as a developer or as an operations engineer, we know that we can iterate quickly, and we know that we haven't got any strange environmental specificities on the build server that are preventing us from doing our job. We'll talk about how the secrets are managed later, but secrets, depending on the application, are just something that are deemed by your organization as exposing information about your deployment. So for a highly regulated financial institution, it may be that the host names of your servers are considered secret. For the rest of us, fortunately, we can get away probably with including those. But again, the boundary between secrets and configuration is blurred and context dependent. And then what's this doing? The build tools image is just doing something with the API of the cloud provider. We'll get into that later on. So single availability zones rarely fail in isolation. Instead, we see catastrophic events which tend to take out more than just a single reason. But applications should be designed to mitigate that level of failure. So we should be deploying to multiple regions, for example. So the solution to entire region failures rather than availability zones, it's global deployments. Geographically distributed systems pose a huge number of hard problems, especially data replication, that put them out of the reach of small teams. Why this approach now? Well, we are all moving into a cloud-native world. Just some definitions. Cloud-native kind of means it uses containers broadly. Provisioning and deployment kind of used interchangeably. So for the purposes of this talk, we'll try and say provisioning is the configuration, and deployment is actually putting something onto it. It's configuring the infrastructure. It's, as I said, these are kind of mutable terms. And back to cloud native. Not again. All right, this is a load of otters chasing a butterfly. It's wonderful, honestly. I'll publish these afterwards, so you can independently verify my claims of the quality of these memes. Right, so yeah, the ubiquity of containers as a bundling and packaging mechanism allows an engineer to run exactly the same locally as on the build server. But the infrastructure still needs to be deployed. So for that, we have Terraform. Terraform, for those who don't know, abstracts away cloud provider APIs by providing a declarative language on top. That declarative language actually essentially formally verifies itself before running, so that complex interdependencies can be modeled as a graph, and we don't have the eventual consistency of the cloud provider APIs occurring off remotely, and it catches a large class of problems before we actually start sending commands or API calls to that cloud provider integration. So it really reduces the difficulty of managing a lot of infrastructure. This approach of just bundling everything together can be used for operations tools or developer tooling or anything else that would previously have been distributed without its runtime. Having the container environment, it seems like a no-brainer, but really enables fast iteration and removes this annoying pain of not running the same version remotely as you're running locally for development, which with Terraform can be a real problem. We probably know excessive use of configuration management tends towards actual programming. This risks bugs. Essentially, manual changes to a server can render already tested changes unstable, and different starting points can leave servers with configuration drift. I hope that's enough to get the point across. So this may not be a problem when undetected, but can cause significant problems when operating at scale. So, configuration management tools, we kind of know these. By using these to configure a blessed or golden base image, instead of configuring servers after they've been deployed, we can get a number of guarantees. We can scan those images, we can test them for vulnerabilities, we can harden them, we can make sure they're compliant before we push them out into our infrastructure. Now, this applies both for a machine-based image like an AMI, as well as for containers, for deploying containers into production. Having that pipeline just ensures that we have these test hooks in place. So it may be the configuration management suits smaller teams better, or that very large deployments pay too high a cost to actually redeploy servers or entire VMs. But meter-proofing kind of aims for a sweet spot, as little running configuration management as possible, and as many immutable artifacts in a registry, repository, or other data store. Of course, we've got to test everything from the smallest unit to the whole system. That means our good friend Jenkins. Again, everything triggered and run via a build server. In short, the core principles of continuous delivery. These risk-reducing practices are well established for development teams, but are kind of far less obviously, or maybe more rarely used in infrastructure engineering. So, with the fundamentals there, with all deployed code baked into that Docker image and the build tools image, this API wrangling then just becomes Terraform requesting a desired state. And then we've got multiple environments that we can hang off the back of this. What this means is by having the build server run this whole stage, then not only do we have full logs of everything that's been deployed, no more allowing developers to run infrastructure changing code from their local machine because you just don't give them the credentials. It also means that we can have cookie cutter re-implementations of production-like environments because we do give developers credentials to their own VPC or ideally their own account, depending on how many, depending on your sort of account billing hierarchy or how many people you want to enable. And then you can start punching out cookie cutter style implementations of, say, production infrastructure and make those changes, experiment. These are when things like pulling scrubbed data back from production make sense for your application because there are so few differences between what you've deployed and what's pulled down from production that you're able to operate with far more certainty that when you do push those changes to production, you will have a consistent experience with your development experience. Of course, this can be extended to set up and tear down those environments daily, shifting left, bringing pain forward. They're all the same principles as we use for continuous delivery, just applied to infrastructure and sort of more difficult non-deterministic, semi-non-deterministic things. That obviously highlights the importance of not only packing the build tools into this container, but also all the tests that run with it. So a single container, a single version, cryptographically hashed so you know exactly what's in there, can be used to deploy, verify, and then tear down your infrastructure again in CI. Again, just bringing the pain forward. So I've spoken in generalities. Let's speak of specifics. How big is this meteor? Now, I'm not an astronomer or physicist, but I do like meteors. So I hope these videos work. Let's see. Maybe. It's difficult to tell, isn't it? I suspect. Let me just try one more thing. Excuse me. I wonder if my VPN has kicked in. Nope. I'm going to take a risk and just reload this mid-talk. Let's see if that paid off. If it doesn't show up, it doesn't matter so much. It's so that has cached the rest of the slides. Never mind.
Where the play button at the bottom there?
Those are for the slides, not for, he says. Yeah, that's an auto advance. Sorry about that. Never mind. So anyway, the space rocks that we're interested in are meteoroids or asteroids. What did I do there? Yes, meteoroids or asteroids. I do apologize. Okay, I'll just go back to the pipeline comp and back on the internet, so that will turn back up in a minute. Very sorry for this unscheduled break. Okay. Okay, so asteroids generally orbit the Sun in the main asteroid belt between Mars and Jupiter. And meteoroids are debris from asteroid collision. Oh, would you look at that after all this time? Oh, well, who would have thought it? So, yeah, meteoroids are the debris from asteroid collision. And some get close enough to Earth to enter the atmosphere. When they start to vaporize in the upper atmosphere, they become meteors. Most of these burn up, but some of the rocks that hit the Earth are reclassified again as meteorites. But they don't need to hit the ground to cause damage. This is the aftermath of Tunguska, Russia, which in 1908 was victim of what is supposed to be an airburst. 770 square kilometers of thankfully unpopulated woodland was flattened. And that goes off at an estimated 15 megatons or 1,000 Hiroshimas. It was only 4 hours of Earth rotation from St. Petersburg. So this has been estimated as a sort of 1 in 100-year event. And there's been nothing of comparable size since, which may mean that we are due another impact. Or from a solar perspective, in some ways we are guarded by our bulky neighbor, Jupiter, which pulls in a lot of potential near-Earth objects. And as you'll see from this eventually, the size of the collision here would have wiped the Earth out. So that huge gravitational pull really helps to defend us. We also use a global array of microphones which are used for detecting nuclear strikes to track meteors. So we know when they hit the Earth, broadly. So if one of these does hit the Earth to threaten our data centers, how big is big? Well, about 25 meter meteors will probably burn up in the atmosphere. A kilometer plus meteor is an extinction event. So we're going to guess about 400 meters width of meteor will be enough to damage more than one Amazon data center, which are about 40 miles apart by design. So that is a nuclear explosion superimposed onto London. Very sad that that didn't make its way in here as well. But nevertheless, some of this is, of course, scaremongering. We do tend to catch these meteors. However, with the Tunguska event, potential 100 years, one never knows. So how do we reduce the impact of these? Well, we can reduce humans, because 22% of network outages are the fault of a human. So again, Terraform sort of heralds the new way to get out of this bash entanglement. And here we are. This is an example of a Terraform resource. It's just declarative, and we can see what we're doing is defining what we want the cloud provider to do for us, not the mechanism by which that's enforced. Of note is Terraform, as I said earlier, will walk the dependency graph and give us fast feedback when we've made dependency mistakes. For example, trying to refer to the value of something in ourself, or a cyclic dependency where something depends on us, but we're then trying to depend on it. And gives us a lot of primitives by which to order and structure these things that significantly reduce the significantly reduce the difficulty of scripting against a remote API, for a cloud provider API. So this provides us with the base for a secure, repeatable, fast-to-iterate pipeline that can be depended upon at 3 in the morning when all the systems go down. So again, going back to this image, the desired state changes here handled by Terraform. Terraform run from the build tools image. It's worth mentioning the secrets repo at this point. That can be handled in a number of different ways. That could be an integration with the cloud provider like KMS. That could be a Vault integration. That could just be GPG being used to encrypt all the keys. Of course, GPG is just an identity primitive. It's equivalent to using an OAuth provider or similar to actually retrieve those keys. However that's done, they can be baked into the build server. That is a likely point of escalation. And it should be noted that anybody with access to a repository that is being built by the build server effectively has the same level of access controls as the build server running the code on their behalf. It's kind of a no-brainer, but if that build server can deploy a load of infrastructure and my machine is compromised, someone's able to put the code they want into the Git repo the build server builds. So there are various things we can do to build trust backwards on this, one of which is signing Git commits with GPG. That just attaches identity to the Git repo. It's still not a fully featured story because things like GitHub and GitLab will give you a verified tag, but they will not ensure that the committer is in a pool of users from a public key store, for example. So yeah, just always worth considering where these secrets are baked in. And with each environment tagged with the version of the repo that it's built from, we have, as I said, this cookie cutter approach, and we're continuously delivering environments. There are some complexities when running Terraform at any sort of significant scale, one of which is sharing states between different jobs. This is to avoid having one single Terraform map that covers the entirety of the infrastructure that you're deploying. By segregating that into logical groupings and then sharing state between them, we can decouple those from each other while also making use of their outputs. Mesmerizing, isn't it? And then, of course, restricting environment access. Once we have this cookie cutter approach where production can just be brought up at any time within reason in different accounts or different VPCs, then we can start to restrict access to those environments. We can, for example, say the keys to deploy to production are uniquely within Jenkins or provided to Jenkins via Vault or KMS or however that works. And the only way that that can be authorized is with RBAC based on the fact that the user initiating has permissions to then ask Jenkins to do it. They don't have the keys to go and do it from their local machine because allowing people to operate quickly and, again, with impunity does mean that everything should be made as safe as possible by default. It's kind of, again, self-explanatory to say, but by significantly reducing the amount of places that my laptop can access in my infrastructure, I reduce the potential for mistakes. As I've said, the build server is always a likely point of escalation and should be pen tested in itself. Yeah, this provisioning of identical environments also means that we have somewhere demonstrable for people to work in tandem and in parallel with each other, reducing the contention on whatever existing environments are present. So, kind of been through some of these, but per engineer dev environments reduce that contention for resources. Dev and test infrastructure can be torn down overnight, torn down on weekends. This means that the sort of proliferation of environments that we're encouraging with this approach actually has some financial benefit to the organization as well, because everything can be stood up with spot instances or reserved instances, dramatically reducing the cost of deploying the infrastructure. Then also tearing it down, we're operating at far less, hopefully far less cost than initially. Safer but more testable deployments. This is all about ensuring that when all of these things are really necessary, like when we've had a regional failure, for example, and we come to test our backups and our redeployment scripts, everything has been tested so many times by virtue of being stood up and torn down daily that any non-determinism or flakiness or any race conditions that we have, all kind of flavors of each other, are surfaced, covered by tests, and then fixed way back when, rather than in the high stress of disaster recovery events. Prompt security keys rotation. Well, this comes in two parts. One is that by automating access keys, so for example, creating a new user and generating their keys, we know that we can just remove the user and the keys disappear. Also, the other extreme is by having the whole environment deployed from scratch. Instead of rotating the keys in the event of a breach, assuming that we've done the forensics that we want to do, we can just deploy another environment with different keys and decommission the first one. And continuous security by default. All these techniques, relentless automation, really lend themselves to a continued aggressive chasing of automation for security principles. So this means automating the low-hanging fruit that pen testers generally come in and find and write you up on. None of that stuff should be present in a pen test report. That should all have been automated, it should be run on a timer, and it should be run on check-in so that we know not only the minute something changes via a code change, but also the minute that our environments deviate from what has been signed off on by somebody working, say, in a console rather than through the escalation and promotion of a build process. And yeah, just to digress on security very briefly, a point-in-time pen test is severely limited. The advantages of continuous security are taking that same compliance and audit and just bringing it back, shifting it left, running it constantly. So what are the drawbacks? Well, there is a significant upfront cost to this. It is difficult to achieve. Highly skilled teams are required. But ultimately, we have to deploy everything in an automated fashion in order to be reliable, resilient, and rugged. There are only a few minutes left, so these slides will be available, but Adrian Coiler basically comes up with some great papers, believably. You know what's missing there. How is this? I wonder if my clicker's now gone. Let's see if I can click through this way. All right, that works. Yeah, so Snowflake environments are obviously a risk. They are far less likely to be secure. Silicon Valley's infrastructure Meteor-Proof? Absolutely not. This is a Snowflake environment because they can't recover from a disaster event. So this section is really quite documentation heavy, but just broadly, we need a subsystem to deploy into a standard AWS IAM parent account configuration. And everything is generated, all the users are in the IAM account. Like I said, these are all quite self-explanatory and a bit deep, so I will just zoom through them. There are loads of different ways to deploy Kubernetes. They are, a lot of them linked at the back of here. But these are all the best practices. So the build tools actually look a bit like this, baking everything in that we need. The test suites here, obviously bypassing the API because we want to just be testing the acceptance testing the application as it's deployed. This is a suggestion for how these things could look. Again, apologies for the speed I'm going through these. And then we need meta configuration as well so that we know not only what to build, but also the specificities for each environment. Again, some suggestions around how this could look. We've spoken about what a secret is. Accreditors are the source of truth. Abstracting too much stuff as a secret means that parsing the code becomes very difficult. Again, there's some detail about how this actually looks. It is a bit dry, and it's very important to prevent any of the secrets getting pushed back. This was mentioned briefly in the GDS talk just beforehand, but running pre-commit hooks with continuous key scanning tools to make sure we don't commit anything when things are being committed as code is of paramount importance. Just some other things there to explore. Is it worth it, we ask ourselves? Well, cloud-native applications expect a standardized, homogeneous platform on which to run. Bootstrapping a Kubernetes cluster is rapidly becoming an API call, and even that should be triggered from a build server. Testing network routes is really difficult. Again, requires automation. This will keep on happening, so I'll just move on. Continuous security, again, I've touched on, sorry for the speed of whizzing through this. Why this is important? Well, again, it's kind of self-explanatory and dovetails nicely with continuous delivery. This is why it's so important. Again, I've sort of covered this in previous slides. And these are all useful tools that can be used to test the conformance of your environment. The Linux exploit suggester is probably coming at it from a slightly different angle, but always interesting to see what CVEs you are vulnerable to. Of course, we've always got to run IDS on these systems as well. Just some other recommendations here, the open source versions thereof. We've written a tool at Control Plane, which is basically static analysis. So if you post that pod with read-only with a privilege true, it'll give you a score, and you'll get a -30 for that because you can't run privileged pods. It breaks the container security model. So with all that being said, don't get caught out. Be proactive and preempt what's coming and Meteor-Proof yourself. So when the meteor hits, we're all able to rebuild as if nothing actually happened. So there is a brief summary and some extra notes at the end. Thank you for listening.